Hello, hello, intrepid calculus explorers. We are back to topic 5, antiderivatives and integration, and this is kind of our, I don't know, maybe our third of the way point through this unit, maybe closer to halfway, but I kind of picture it in thirds. This is our last day that we'll be dealing with indefinite integrals, where indefinite integrals are essentially an antiderivative. You get an equation. And then starting with day 68, we're going to get into those definite integrals. That's kind of the second third of this topic. And then the last third is putting them together. How do indefinite and definite integrals mix? But that's more a vision of the future, so let's go ahead and start with the opener. In fact, since today's topic is additional integration topics, ultimately what we're trying to do is learn extra tricks that will help us take antiderivatives. Because derivatives are pretty straightforward. It's here are a set number of rules. You can use those to take the derivative of everything. But integrals really struggle. Lacking the product rule, quotient rule, and chain rule for antiderivatives makes it so there are some where we can't take the antiderivative and others that we really have to rewrite in order to be able to do that. So the first 2 out of 4 of these pages are actually review from Algebra 2. So we're going to see what you can do on this opener, and then we'll come back together. So there are 2 quadratics here that we would like you to solve without a calculator and without the quadratic formula. So we'll see what you can do, and then we'll check in shortly. Ready, set, go. Okay. We're back. Hopefully you had some success. I do have to say that in the past my students generally do not have a lot of success with this, and that's because kind of the way that we teach this topic. So how do we solve these? Well, I'm actually going to demonstrate them down below, and I'm going to give you 2 different ways, 2 different methods that kind of lead to the same end result here. But ultimately what you need to do to solve these is to complete the square. You might say, well, wait, I factored this. These are not factorable with nice numbers, with integers, right? You might have said, oh, it's x plus 6 and x plus 1, but 6 times 1 isn't 7. And you're like, maybe it's 7 and 1, but 7 plus 1 isn't 6, and it doesn't work. I promise. So when you have something that's not factorable, you have 2 options. You have the quadratic formula and completing the square. And there are actually a lot of places in the world that don't focus much on the quadratic formula because completing the square is a little bit more of an efficient way to do this. And it's less memorization. Instead of negative b plus or minus, it's just you just complete the square. Now, I also realize that many of you have probably forgotten how to complete the square, and again, that's kind of, I won't blame us per se, but I'll blame the system a bit. You first learn how to complete the square in Algebra 1, and then you probably never do it in geometry, and then you do it right at the beginning of Algebra 2, and then you don't do it again for the rest of the year, and then you might do it for like a class in trigonometry, and then you don't do it for a year, so it's very kind of touch and go. So here we go. What is completing the square? Well, completing the square takes a trinomial or a quadratic polynomial and converts it from standard form that I just boxed into vertex form. Now, there are 2 ways to do this, and I'm going to show you both. I'll show you the classic way, and then I'll show you the way that I do it. So, classic way first. The classic way sets something up like this. They say something like, okay, to complete the square here, we're going to have this guy. It's going to be squared. We have an x, and actually, maybe I should do it better. So they do something like this. They say, okay, we have x squared plus 6x plus something, and then there's a plus 7 over here. Some people move the 7 over to the right side, but it's optional, and I'm not going to do extra. And then they say, okay, well, how do we figure out what goes in the blank? And then there's a formula for it, right? And they say, okay, we need to take this 6, and we need to take half of 6. So I'm going to do half times 6. That's 3. And then you need to square that. Maybe the arrow should go the other way. So we went half of 6, that's 3, and then 3 squared gives you 9. And then this now factors into what we call a perfect square trinomial. If you're used to factoring tiles, it makes a square, like literally a square, even amounts on each side. And so we can factor this into x plus 3 times itself. Whenever you complete the square, the factored form is always something times itself. Plus 7 equals 0. Now, there is a bit of an issue here, and I should leave a blank because I'm going to change this, in that we just, in order to make this a more perfect union, more perfect trinomial, we randomly added a 9, right? We said, okay, let's just put a plus 9, and now it factors. Well, that would unbalance the universe, or at least the equation, and that's a no-no. So there are two ways to do this. If you add 9, you can also subtract 9, because then what are you really adding? Well, you're really adding 0. So if you add 9, a lot of times you'll see people put a minus 9 somewhere on that side as well. I'll keep this over here, just to keep everything balanced. Other times, someone will say, well, in order to keep everything balanced, you add 9 to one side, so you have to add 9 to the other side. And that's true as well. That also keeps things balanced. Realize that you could move this over and it becomes a minus 9. So it's the same thing, whatever you'd like to do. If you want to move it all to the right side, cool. Keep it on the same side, cool. I don't really have a preference because I do this differently, so ultimately up to you. How does this help us solve? Well, it's going to take two iterations, or two instances, I guess, of x, and then because it's multiplying by itself, this whole thing condenses down to x plus 3 squared. 7 minus 9 is negative 2. And from here, it's just a matter of isolating x using SADMAP. So we add 2 to both sides. I'm going to run out of room, but that's okay. We're going to take a square root. Whenever we take a square root, there are two answers to that. We need the plus minus. And we finish up by isolating x by subtracting 3 from both sides. And convention says we put the square root at the end. And there's our answer. Two answers, rather. 1 plus, 1 minus. If you'd done the quadratic formula and reduced it down, you'd get that answer too. And sometimes the quadratic formula is clunky, and it's kind of hard to reduce it down there. You might say, well, wait, where's the over 2a? Well, that gets reduced out of there. Okay, so there's the first one. Now, I did promise you two ways to do this. So let's take a peek at the second way. Now, the second way really hinges on you having a good understanding of what something squared means. So here's what I mean. What I'm going to do is I'm going to go straight from here to the answer. And when I say to the answer, I mean I know that the answer is going to end up looking like this. So what am I going to do? Well, I'm going to start with the thing that is squared. And I know for something to be squared, it really means, and I'll kind of do this over off on the side, and hopefully you can do this in your head later on, it's something times itself, and eventually, when you multiply it all back out, it better equal this guy. Well, of course, it has to start with x and x, because that's the only way that you get x squared. But how do we determine the number that goes in here? Is it dependent on the 6 or the 7? And it's actually dependent on the 6, because this is the only part of the problem that's going to have x. So we have to say, well, how do we get 6? And you're not going to multiply to get 6x. You're actually going to add. So this becomes 3 and 3. It's really half of this term inside. Because if you multiply this out, of course, you get x squared, and then you get 3x and 3x. And then, of course, 3 times 3 is 9. And so this part right here now matches the beginning piece. Right? So I know this has to be x plus 3 squared. And I'll put the equals 0 over here. So then the question becomes, okay, cool. Am I done? Did I perfectly factor it? And if we did perfectly factor, then this guy in red needs to be equal to what we started with. Are those equal? Well, you're probably looking at this saying, no, this is x squared plus 6x, and hopefully you're doing some mental math, plus 9. And this is x squared plus 6x plus 7. They have to be the same. Okay, well, if this gets us 9, what do you have to do to 9 to bring it back down to 7? Well, you have to subtract 2. So this x squared plus 6x plus 9, if you put a minus 2 here, this keeps it the same as the original problem. And so you are certainly allowed to rewrite these one after the other. And so now I have taken this and written it as something that is the same, and by doing that, we have completed the square. So again, dependent on you being fairly good at some mental math, you can always write it out like I did over here, but I don't normally do that. And then the solving is, of course, the same, right? The solving, exact same steps, you end up with the same answer. Cool. That's when a is 1. And honestly, the majority of time you do this, a will be 1, but it's not always. So let's try both of these in a second way, though I'm going to start with my method first, and then we'll go back to the other. My method because why not? And then we'll see what we can do from there. So the way my method works is I always make a 1. Okay? So I say, well, I'm going to divide everything here by 4. So I'm going to pull a 4 out. It's going to be x squared plus 2x, nope, plus 1x minus 1/4. You're like, ew, that's kind of gross. And you're right, but it will go away at the end. So here we go. My method says, well, if this is going to factor, it's going to be x plus something squared. Well, plus what? The two things have to add up to 1. I think this has to be a 1/2. 1/2 x plus another half x gets you 1x. Cool. And then we say, okay, well, at the very end, 1/2 squared is positive 1/4. This says negative 1/4, though. We're like, drat. How do you get from positive 1/4 to negative 1/4? Well, you start at 1/4, you subtract a fourth, that's 0. Subtract another fourth, that's negative 1/4. So we had to subtract off 2/4, or 1/2, I think. So this is positive 1/4, and we need to subtract off a half to keep this piece equal to the inside up above. Then I'm just going to redistribute our 4. So the 4 distributes here and to the guy at the end. So we end up with 4 times x plus 1/2 squared, and half of 4 is 2, equals 0, and we have completed the square. We might as well solve this one. So we add 2 to both sides. And we're also going to divide by 4. So add 2, divide by 4, that's 1/2. No, divided by 4. That's 1/2. Take the square root of both sides. This one's pretty gnarly, isn't it? Who picked this problem? Plus minus square root of 1/2, and then subtract 1/2. So negative 1/2 plus minus, distribute the square root, so 1 over the square root of 2, or root 2 over 2. And we're there. You do not have anything this terrible today, I promise. But we should remember completing the square. Who knows, maybe you guys have the ACT or SAT coming up, and you'll probably have a problem like this on there. So let's try the air quotes real way, end quote. And the real way does something like this. There's a few ways to do it here. I'm going to go ahead and add 1 to the other side just to give you a different look at this. So we have 4x squared plus 4x equals 1. Okay, and then you were going to factor the 4 out. So it's going to be x squared plus 1x plus a blank equals 1. And sometimes they'll say, well, if you add a blank there, you have to add a blank to the other side. Maybe you've seen it done this way. How do we figure out the blank? Well, we take half of 1, that's a half, awkward, and then square this. So half of 1 is 1/2. 1/2 squared is 1/4. Okay, now the tricky part here is you still have to factor this. And I do have to tell you another shortcut. To factor this, it's not too bad. It is always just this guy that's right here. So it's going to be x plus 1/2 squared equals, and we should probably remember this other side. So you might remember I added 1/4 here, so that doesn't mean I add 1/4 to the other side because I'm not adding 1/4 on the left side. Technically, this 4 will have to get redistributed at some point, and when we do that, 4 times 1/4, oh wait, that's 1. Technically, we're adding 1 to the left side, so we need to add 1 to the right side. And so 1 plus 1, of course, gives us 2. And now we are back to the same situation as before. So however you want to complete the square, that's fine. I'll predominantly be using my method, but it's just completing the square. So when I say complete the square, do it any way you can, and you should be good. That is the first part of our Algebra 2 review. The second part has to do with long and synthetic division. So I'm going to go ahead and give you guys another chance to pause me and see if you can remember what to do here. Your goal is to prove that this divided by this equals what's on the other side. So you can hold off on the other side, maybe even pretend it's not there, and your goal is really to divide x plus 1 into x squared plus 4x minus 2. And when you do that successfully, you should get the right side as an answer. So good luck, pause me, and we'll come back together. I will show you 2 ways to do this, and then we are finally ready for calculus. Ready, set, go. Okay, we're back. Now, if you had success, congratulations. You can probably skim through this next part. If you didn't have success, you should definitely watch this part. So I'm going to show you that same problem down below, but I'm going to show you in 2 ways. I'm going to show you the way that works every time, which is long division first. And then I'm going to show you synthetic division, which is generally faster, but there's some limitations on its use. So let's start with long division. To do long division, we'll rewrite this first, right? I always think of this guy as like sliding over, and this one slides next to it. So we're dividing x plus 1 into, try not to make a square root here, into x squared plus 4x minus 2. And I do have to tell you, I never leave enough space up here for the answer, so hopefully you left some space. I think I did okay on this, but we'll see what we can do. Then we start with the first term, and we say, okay, what do we need to multiply x by to make it match x squared? You're like, well, x times x is x squared, I think, and that's true. But we don't want to put the x over the x squared. We want to keep all of our like terms lined up in a column, so we'll put the x over the 4x because they are like terms. And then we distribute, right? X times both of these, x times x is x squared, keeping those like terms in a column. X times 1 is 1x. Nifty. This is just like long division. Once you have multiplied these together and got this guy down here, the next thing, of course, you do is subtract. And this is the big deal breaker, big mistake bringer for many people. They forget to group this in parentheses when you subtract. So really, we are subtracting x squared. So, of course, that will be 0. But then we have to do 4x minus 1x, which is 3x. What's the last step of the long division process? Well, we bring down the other term, which is a minus 2, and then start again. And now we say, okay, what times x will give us 3x? And I think 3, so we're going to distribute this. 3 times x is 3x. 3 times 1 is 3. Don't really need to put the 0 here or the plus. And then we do our same thing. Now we're going to say, okay, let's subtract this. And then we do 3x minus 3x, that's 0, which we don't need to write. Negative 2 minus 3 is negative 5. So there is a remainder of negative 5. But remainders is really baby division. And it's not baby division, it's like third grade division. Hopefully by the time you get to fifth grade, you stop writing r dot something and you start putting this as a fraction, right? We have negative 5 left over of the x plus 1 that we divided in. So how do we write that? Well, we take our x plus 3 and we say that went in nicely, but then we have a remainder that is added on, or because it's a negative, we'll subtract it on, of 5 parts of x plus 1. And you should notice, of course, that that is our answer up above. Some people get confused by that because we've done a huge disservice in how we write mixed numbers, right? If you wanted, I know this is a little sideshow, you could probably skip this if you wanted, but if you wanted to divide something like, I don't know, 6 into, let's say, 14, whatever. 6 goes into 14 twice, 2 times 6 is 12, minus, and we get a 2 here, so this becomes 2 remainder 2, and you're like, yeah, but doesn't that mean 2 and 2/6? Here you subtracted. How come you didn't put something in between the 2 and 2/6 here? Well, we did. Just the way we write mixed numbers is a travesty. We put these right next to each other, and it's the only time I can think of in mathematics when two numbers are next to each other, and it doesn't mean multiply. This doesn't mean 2 times 2/6. Really what this means is 2 plus 2/6. But someone decided with convention that why would you write it like that when you can write it more simply? Well, because it makes algebra look crazy then. So don't forget that there is always a plus or a minus, and that's why we have the minus up here. I mean, you could try writing it as x plus 3 and negative 5 x plus first, but nobody would understand what that means, so don't do that. Forget any of this happened. Okay, awesome. Cool. I did promise you synthetic division as well. Synthetic division, I will say, only works when you have 1x plus minus a, so this is like 1x plus 1. Technically, it does work when this is a number besides 1, but it gets a little bit weird, and especially if there's a power here, it gets really weird. So I suggest that synthetic division is a good tool, but use it sparingly, and only when you're doing these nice first degree factors, x to the first power. So how does synthetic division work? Well, this is always the cool one, right? We do something like this, and I always like to start and say x plus 1 equals 0, where essentially you can do some other division and some cool stuff here. We solve this and we find x equals negative 1. And that's what's going to get divided into all of our terms. What do I mean all of our terms? Well, we have x squared plus 4x minus 2, which means there is a coefficient of 1 in front of x squared, 4, and minus 2. How does it start? Well, we bring this guy down, and then we multiply. So negative 1 times 1 gets us negative 1. And then we combine like terms. So 4 and negative 1 when you combine makes, of course, 3. And then we start again. Negative 1 times 3 is negative 3. And then we combine like terms. Negative 2 minus 3 is negative 5. And then we're done. We draw a cute little line right here. And then we reduce each of these powers by 1, because essentially we're dividing out an x from each of these powers, so all the powers reduced by 1. So instead of this 1 being x squared, now this 1 is x. This was a 4x, but it lost an x, so now it's just a 4, or in this case just a 3. And then we have the negative 5, which is going to be a remainder over this x plus 1. And then we have our majestic, easy solution. So certainly synthetic division is a little bit quicker than long division, but honestly not by that much, by like 20 seconds, and maybe even less than that. And synthetic division doesn't work every time. All right, there is our Algebra 2 review. So Algebra 2 teachers, hopefully I didn't muddle that too badly. It's been a few years for me. Let's get into the calculus part. Man, oh man. There are two types of problems. This third page has problems that are all predicated on completing the square. And then the fourth page has problems that are all about long division. We should probably close read these directions though. For each of these two topics, 2 pages, find the general antiderivative. That means plus c. Please note that although there are topics listed for each part, completing the square versus long division, there are 2 integrals on part 2 which do not fit the theme, but you should still know how to evaluate. So on this second part, there are definitely going to be some integrals that may not require long division. And we're going to talk about how you know when something requires long division and when it doesn't. Now, I'm not going to do all of these. I'm just going to pick these last 2 because I think they're representative, and then you guys can try the other 4. I do have the full solutions posted on Teams, so you can see all my work all the way through. But let's kind of get a feel for the general pattern as we go through. It looks like they've written dx as the numerator of every single fraction, 4dx here. And then it looks like the denominator either is a trinomial without a square root or a trinomial with a square root. All right, well, let's try to complete the square on one of these. Let's maybe look at this guy over here. Okay, so this is problem 5. As we go through, before I even think about completing the square, I'm hesitant because I'm like, a is not 1, life's going to get weird. I think I gave you all of these where a is going to be 1, so don't stress. You're like, but a is not 1, I see it. You're right, so let's just rewrite it. So I'm going to move that dx off to the end so no one feels confused by it, and then I'm going to factor out a 2. So x squared minus 12x, ooh, half of that's got to be what, 37? Seems like a thing. Yeah, that looks pretty good. Cool. All right. Well, then I think we can even rewrite this one more time because there's a 1/2 we can factor out. I don't want that in the integral. So we have 1 divided by x squared minus 12x plus 37. Let's see. Can we factor this? I think 37 is prime, honestly. I don't think we're going to break that apart. 37 and 1 won't make negative 12. This must be the completing the square part. So let's do that. So to complete the square, I know it's going to be x minus 6 squared. That's the only way you get negative 12x. Negative 6 squared is positive 36. How do we turn 36 into 37? Oh yeah, you add 1. And look at that. I completed the square like a champ. So that's my method. It's patented. Honestly, a student made it up and then I stole it. But that was like 7 years ago. He probably doesn't remember. It's fine. Okay. Why did we just complete the square? That looks weird. Well, what if instead of x minus 6 squared, it was just 1 over x squared plus 1? Oh, that's an antiderivative we should know. 1 plus x squared in the denominator. Isn't that inverse something? Oh yeah, that's inverse tangent. And using our awesome guess and check skills, my guess is I can just do the antiderivative, inverse tangent, and write this as x minus 6, with of course a plus c at the end. Thinking about this derivative, the derivative of this I think will be this guy, and there's no chain rule involved because the derivative of the inside is just 1. So that is our answer. Every derivative that involves completing the square will either be inverse tangent or inverse sine that you guys will see on the AP exam. I think, and eventually I'll probably have to eat those words, but those are all the examples I was able to find, so that's what I'm going with. So we see this, there's no square root, you're like, okay, that's probably inverse tangent. However, we see problem 6, there is a square root. You're like, that's probably inverse sine. Okay, so let's make it look like inverse sine. First thing, get rid of that 2. Nope. And let's also move the dx to the end, and let's rearrange this weird thing. How about we write this as negative x squared plus 4x minus 3. It might help you to remember what the derivative of inverse sine is, right? So if we take the derivative of inverse sine, arc sine, then that becomes 1 over the square root of 1 minus x squared. And you're probably looking at this going, how the heck is that going to turn into that? Well, magic, or completing the square. Mathemagic, if you will. Let's get to it. Before I complete the square, I don't like that a is negative, so I'm going to factor that out. So we have 2 times the integral of 1 divided by the square root. Let's pull that negative 1 out. And then we have x squared minus 4x, switching the sign, plus 3. Let's complete the square in here. There's a dx as well, sorry. So 2 times the integral, 1 over the square root. There's still this negative 1 hanging. And to complete the square, I think we'll need a second set of parentheses here. We have x minus 2 squared. That's the only way you'll get your 4x. 2 squared is 4, but we want it to be a 3. So what do we do to get from 4 to 3? We subtract 1 dx. From here, I'm going to redistribute the negative 1, and we'll see what happens. Now, I imagine you'll probably skip a bunch of these steps when you're going through the first once or twice. You're like, okay, this is a long process, but as you see shortcuts, please take them. If I distribute the negative 1, it becomes negative x minus 2 squared. Distribute the negative becomes positive 1. And now we're closer. But the positive 1 over here is written first, and so it might make you more comfortable to rewrite the denominator with the positive 1 first and the x minus 2 squared second. And looky-loo here, this is so similar to the guy up here. Just instead of x, it's x minus 2. I bet we can skip right to our answer. 2 times the inverse, that was a c and an s at the same time, inverse sine of x minus 2 plus c. Whew. Would you have imagined this became that at the beginning? Because I certainly wouldn't have. That would be a tricky problem. Now, where do these problems show up? Multiple choice. I've never seen one of these on a free response. I'm sure they could show up, but that just seems mean. So, yeah, I've only seen these on multiple choice and just in the last couple years. You might see one of them. Never both, just one. So I did 2 of those. I'd suggest you probably pause me and try the other 4 right now while that's fresh in your mind. And then once you're feeling like conquering the world, you can move on with me to the next page. Okay, so we are on to this next page. I did mention on the previous page that 2 of these problems don't actually fit the long division theme. But then the question becomes, how do we know when to use long division? Well, I'll tell you. You want to use long division when the denominator is smaller than the numerator, right? We kind of think of this as fractions. So if I had something like 4 divided by 2, that would be fine because 2 has room to go into 4. However, if I had 2 over 4, I don't want to divide 4 into 2. That's very strange. Right? We'd probably just leave it as a fraction. So when the power in the denominator is smaller than the power in the numerator, long division's a go. And so I'm going to do long division or synthetic. And actually, let's take a look at the problems that I picked here. I'm going to go ahead and actually do synthetic division for this one because it's the only one that I picked that has a 1 in front of the x down here and also has x to the first power, right? None of the others have that. So the others seem to me either to be long division or ones that don't fit the rule. So here's our long division. Maybe I'll kind of split this in half. Hopefully that's enough room. So we need to divide x plus 1. Oh, and I did it again. Didn't leave enough space for the answer. X plus 1 into x squared plus 4x minus 2. And you might be asking, wait, why are we doing long division again? Well, it's because I don't know how to take the antiderivative of that. We have 2 functions that are dividing, and we don't have a quotient rule for integration, and we can't divide until we can rewrite this as something without 2 functions dividing. So also, it's because I told you to use long division. So humor me for a second and let's see what happens, right? So working with this, x times x is x squared, x times 1 is 1x. We subtract these, 0, 4 minus 1 is 3. And yes, I am aware this is the previous problem that we did, but either way, can't hurt, right? So what makes 3x? That's going to be a 3. This is 3x plus 3. Subtract that, we get a minus 5. So we can say then that we have, maybe I should do an equal sign, that x squared plus 4x minus 2 divided by x plus 1 is actually the same as x plus 3 minus 5 divided by x plus 1. Whew, let's use that. Integral. This is the same as what we just found, right? X plus 3 minus 5 divided by x plus 1 dx. I think we can actually do this antiderivative now. This is pretty exciting. It may help you visualize this if you'd like to put the 5 and then times 1 over x plus 1. It might help you see the derivative a little bit more nicely just from experience. So let's do the antiderivative of each piece. X becomes 1/2 x squared. 3 becomes 3x minus 5. It's a constant times antiderivative of 1 over x plus 1. Well, if it was 1 over x, oh, that looks like natural log, doesn't it? I think it's going to be natural log absolute value x plus 1. You absolutely need the absolute value to get full points. Cool. So we went from here to here. Probably wouldn't have suspected that answer too, a natural log out of nowhere. Well, if you ever have a remainder when you divide, then you will probably get natural log every time on these. So looking at 8, this power is 1 smaller than the numerator, so that's probably a good one to do long division on, or synthetic division. Oh, I said I'd do synthetic and then I did long. Ugh, epic fail, Mr. Grant. What about 9? Ooh, 9. The power is 1 bigger than this one. I think long division or synthetic is not a good way to go there. So, gross. I'm also going to skip 10 because I've already taken up tons of your time. 10, this power is smaller than the numerator. You're going to do long division on it. Don't do synthetic. The 2 is going to make things all wonky unless you're really good at synthetic and you remember how to use that too. And then looking at 12, well, looking at 11, this is 1 smaller, so that's good too. Looking at 12, ooh, this one's definitely not smaller, so I think probably worthwhile going through 9 and 12. Let's see, how do we do these? Well, problem 9, I'm thinking our only other method we learned, if we can't do those two, is probably U-Substitution. U-Substitution works if the power in the denominator is 1 bigger than the numerator, and that seems to work here. So let's take a look at y. And I'm going to rewrite this quickly as 1 over x cubed minus 2 times x squared times dx. The U-Substitution always has to go for the larger power. We've seen that before. So we're going to say let u equal to x cubed minus 2. And the larger power in terms of a fraction for a U-Substitution almost always should occur in the denominator. We usually want to substitute u in the denominator, not in the numerator, and that's because of the du. When we do du over here, right, differential, this just becomes 3x squared, and we tack that dx on at the end. I see this part, but there's no 3, so we should probably divide off the 3, right? 1/3 du equals x squared dx. There we go. This dx is always going to be dx over 1. Always, always, always. Which means when you do the du, this is going to give you dx over 1. The du always has to replace something in the numerator because dx is always in the numerator. So be careful with those u substitutions. You want to substitute u for the denominator in pretty much every case that you can. If you're like, I don't know which one, do the denominator for u. And then the du will take care of the numerator. Okay, let's substitute all this in. So we end up getting 1 over u, right, times 1/3, switching colors again, times 1/3 du. And hopefully at this point we can see this is going to be 1/3, 1 over u is the natural log of u plus c. And replacing that u once more, natural log of what? Wait, what was u? Oh yeah, that's right. X cubed minus 2 plus c. And there we go. Okay. Natural log does occur a lot when the numerator is 1 smaller or 1 larger than, nope, the denominator is 1 larger than the numerator. So there we go. Again, we knew not to use long division because this was bigger than the numerator. We want to divide a larger number into a smaller, a larger variable. Weird. Okay, last but not least, 14. 14 is just a wild card. I like throwing it at you. I don't think you'd ever see this on the AP exam. But it doesn't really fit any of our patterns. Not going to do long division because we can't divide x to the fourth into x nicely. It won't go in at all. We're also not going to, I think, use a U-substitution because if we let, and I'm going to erase this, u equal x to the fourth plus 1, then du is going to be 4x cubed dx, and this is just plain old x. So what do we do? Well, I told you this was a weird wild card, so check this one out. What if I rewrote this before doing an antiderivative as 1 over x squared squared plus 1 dx. Oh, I left off the extra x dx. Whoa. Now, couldn't we do a u substitution for x squared and the du will take care of the x dx? If you thought of that, I bow down to you. I don't think I thought of that. I'm pretty sure I found this example in one of our books, and I'm like, that was pretty cool. I bet the kids would like this. And probably half of that statement was true, the pretty cool part. So here we go. Let's let u equal x squared, which of course means that du will be 2x dx. Takes care of most of this. There's an extra 2. Lame. So 1/2 du can replace x dx. And here we go then. Integral 1 over something squared plus 1, something squared plus 1. Oh, I bet we know what this is going towards. Can you guys think of it? I'll factor out that 1/2 too. So 1/2 integral, I'll even rearrange this for you, 1 plus u squared du. And now can we see that this one ends up being inverse tangent? Pretty wild. 1/2 inverse tangent of u plus c. Or continuing through, 1/2 inverse tangent, no longer u was x squared, plus c. Definitely a tricky problem. Again, probably almost certainly beyond anything you'd see on the AP exam. But I think it's always nice to look at other techniques. And really our techniques for calculating integrals come down to, can you calculate it? Do it. If you have division or multiplication, you're either going to be using a U substitution, long division, or completing the square. So thank you for tuning in. You guys do need to finish the rest of these. I do have the solutions posted. Practice that completing the square. Practice long division. I'll do my best to make sure you don't forget before the test because it's kind of a weird niche lesson. Niche? I don't know. And yeah, I'm excited to have you back next class. I will tell you that next class we are going to stop doing this. You'll keep doing these on your independent practices, your homework, and we're going to introduce a completely different, at least for now, definition of the integral. And you're going to be like, whoa, where did antiderivatives go? And actually, I think a lot of people will find the next section easier. We're just going to be finding some area and doing some geometric shapes. Maybe that scares you, maybe not, but tune in next time to see and be amazed at a different definition of the integral.